right, this is numbers 10 through 16. These have to do with friction and some spring problems. So here we go. Number 10, an object that weighs 65 newtons, that is its weight, is right here, is being pulled on a horizontal surface of 48 newtons to the right. The frictional force on this object is 25 newtons to the left. Okay, so here I have my pull force, my friction force, and they wanted to know the acceleration, I believe. Let's see, what is the acceleration? So let's draw a picture, or I did draw a picture. Now let's look at our free body diagram. I have my pull to the right, I have my force of friction to the left, I have force normal, force of gravity, and they want to know acceleration. Notice the two forces in the x direction, 48 versus 25, they are not equal to one another. I will have acceleration, so we will sum the forces in the x direction. It'll equal the object's mass times acceleration. Now let's sum the forces in the x direction. I have one to the right, which is positive, minus the one to the left, which is negative. Rearrange the equation for acceleration in the x direction and plug in my values. Make sure you are in SI units. So the tricky part of this problem is we were not given the mass. We were given the weight of the object, so we needed to remember what the equation of weight is. The weight of an object is equal to its mass times acceleration due to gravity, and we're assuming we're on Earth, so that value is 9.8, and so we had to calculate its mass to be 6.6 kilograms, and that is where this 6.6 kilograms is located, and we have then the correct answer of 3.48 meters per second squared. Be careful to make sure you understand what's being given. Number 11, a driver in a 950 kilogram car is traveling at 15 meters per second, slams on the brake and skids to a stop. If the coefficient of friction between the tires and the level road is 0.8, how long will the skid marks be? We will first draw a sketch. So I have a picture of my car sliding. I have an initial velocity they tell me is 15 meters. They have a final velocity that they gave me was 0. They asked for how far did it take to skid. Okay, then they also gave me the mass, and they gave me this value of mu k, which is the coefficient of kinetic friction. Okay, so if I want to know delta x, notice those are part of my 5, 4, 3, 2, 1, right? So I have delta x, v initial, v final, a, and time. If I have 3 of them, I can find the other 2. So I'm looking for one of those, and I'm only been given 2 of them. I need a third. Well, acceleration is one of the 5 variables. So we are going to use our newfound skills of forces and Newton's second law to solve for acceleration first, so that I can then have my third variable. Well, how do I solve for acceleration using Newton's second law? Well, I got to sum all the forces in the direction that is of interest. So we draw a free body diagram, which I have shown over here. I have force normal up, force of gravity down, and then the only force that's acting on the car while it's skidding, it is moving to the right, while it's skidding, is the kinetic friction force. And that makes sense that I would have acceleration to the left because I only have one force in the x direction, and it's to the left. So I will solve for that acceleration. So I sum all the forces in the x direction. It's mass times acceleration in the x direction, which is equal to the negative force of kinetic friction. It's negative because we assume left is negative. I rearrange that equation, and I find that the acceleration is force of friction over mass. It's still negative. I then plug in my definition of force of kinetic friction, which is on your equation sheet, and you would have, which is mu k times force normal divided by the mass. Once again, I need to plug in what force normal is. And if I look in the y direction, I see force normal has to equal force of gravity. So we plug in the force of gravity for force normal, which is mass times acceleration. Notice my mass cancels, and my acceleration is essentially the negative mu k times acceleration due to gravity, and I get a value of negative 7.484 meters per second squared. This becomes my third variable. Okay, now I have three things. All right, I have initial velocity, final velocity, and acceleration. I can now solve for delta x. The equation that I would use for that is my third kinematics equation, which is on my equation sheet, right? I'm sorry, it's my fourth, how I have it listed here. I'm looking for acceleration. I have the final, initial, and displacement. So that is the only equation that would work for me. And so I can then use that equation to solve for its skid length delta x, which comes out to be approximately 14 meters. That would be in units of meters. Number 12, that is a challenging problem, I would agree. Number 12, an object slides on a level floor, it slows down and comes to a stop. Okay, acceleration is 1.8 meters per second. What is the coefficient of kinetic friction between the object and the floor? So let's draw a sketch. It's sliding, it comes to a stop. If it's coming to a stop, which way is acceleration? It's got to be pointed to the left. Okay, and they give me the question of mu k. So let's draw a free body diagram, which I have shown here. Force normal up, force gravity down, and what is happening? It's sliding. Nothing's pushing it, it's just coming to a stop, and that is the force of kinetic friction that's causing that. They want to know mu k. Well, where is mu k located? It's inside this equation for force of kinetic friction. What if, again, you would have your equation sheet, force of kinetic friction is equal to mu k times force normal. Okay, so there's what I'm trying to find. So I got to sum my forces in the x direction. Okay, add all my forces up in the x direction. There's only one force, it's to the left, that's why it's negative. I've been told the acceleration. Okay, so I've got the mass of the car. Did they tell me? They did not, but that's okay because I don't need it. You'll see. Acceleration, mu k, that's what I'm looking for. I can rearrange this equation for mu k, and sure enough, negative mu mass times acceleration over force normal, which we know is mg in this situation because it's equal to force of gravity. Okay, and then my mass cancels, perfect, didn't even need mass. I had a negative acceleration, so it makes my negatives cancel, which is great because we know that mu k is a positive number, and there it is at 0.18. Again, a challenging problem. Number 13, a 42 kilogram box rests on a surface. It's at rest. It is not moving. It is not accelerating. The coefficient of static friction between the box and the surface is 0.3. I'm at the same time pushing on it with 104 or 108 newtons. It's still at rest though, and they want to know what is the frictional force on the box. All right, draw a free body diagram. I'm pushing to the right. What's pushing to the left? Why am I not moving? Static friction. If I have zero acceleration, which is what they tell me, I know that force applied has to equal that force of static friction. So that force of static friction has to equal that 108 that I'm pushing. It's matching what I pushed. Now, that's number 13. Number 14 is the exact same problem, except I am going to increase how much I push until right as it starts to slip. And once that happens, then we can draw a free body diagram on that. Same exact free body diagram. This is my force applied, which we don't know, and we want this to be right when it starts to slip. So we now know that this is at its maximum, okay, because it's going to start to slip. Now we're going to assume it's right as the nanosecond that I reach it, so acceleration is still 0. So that force applied has to equal that maximum static friction in order for it to slip. Number 15, which again, you have an equation for that. Force of static friction max equals the coefficient, which they gave me, times force normal, which is mg in this case. And we can calculate that. All right, 2 more to go. These are spring problems. We have a force of 30 newtons. It stretches a light ideal spring from 0.73 meters. I have pulled the spring with 30 newtons of force. So here's my sketch, and I stretched it from from its equilibrium position, 0.73 meters. Here's the free body diagram of that. I'm pulling to the right, force of the spring is pulling to the left. They have to equal one another. So I then plug in the equation for force of the spring, which is Kx, you'll have that. And that has to equal my force applied, which we know. They asked for the K constant, so rearrange everything, make sure your units are in meters. They're often given in centimeters, and I can find my K constant to be 41, approximately 41 newtons. Last problem, an object weighs, excuse me, 125 newtons. They tell me the K constant is 650 Newton meters. What is the distance it stretches in meters and centimeters? Well, draw a free body diagram and a sketch. Force of the spring is pulling up. The weight of the object, or force of gravity, that is the same as force of gravity, which is also mg, is pulling down. I know that those two forces have to equal one another because it's sitting there hanging in equilibrium. So there's zero acceleration. So force of a spring is equal to its weight. I was asked for the stretch length. So plug in your equation, or what you know force of a spring is equivalent to, which is K times X. Rearrange the equation for X, and you find that to be, if once you solve it, everything's in SI units, so your answer is going to be in meters, which is 0.192 meters, and your conversion to centimeters is 19.2, because you move your decimal point 2 times, or better yet, multiply times 100. There are 100 centimeters in 1 meter. All right, I hope that helps. For those that were not able to be in class, reach out to me. Our test is on Wednesday if you have any questions.